Now, if these voltage-gated channels can just be open or closed, you might be wondering why the action potential doesn't happen in steps. Why can't we see each channel snapping open or closed in that voltage trace? But remember that when we have a patch of membrane, there are thousands of channels opening and closing. And they aren't deterministic little machines opening and closing at precise voltages. We're working here at the scale of individual molecules. And when things are this small, everything is about probability and kinetics. As with our diffusing ions earlier, when we're imagining the world at a molecular scale, we need to imagine everything jiggling and jostling under the constant influence of thermal noise. The channel opens or closes when these random fluctuations in energy allow it to shift from one state to the other. Molecular reactions and conformational changes like this are usually more stable in one state or in the other, and the reaction tends to drive towards the lowest energy state. But at least for reversible reactions, both the forward and reverse reactions still occur sometimes. It's all a matter of their relative probability. So when we say that the channels are voltage-gated, what we really mean is that the probability of the channels being open or closed is a function of voltage. Our voltage-gated sodium channel, for instance, is more stable and in some sense happier in the open state when the voltage is higher. And it's happier in the closed state when the voltage is more negative. But it can still be open even when the voltage is low, or closed even when the voltage is high. It's just less likely. So the upshot is that not all channels of a given type are open or closed at any given instant, and averaging over the action of many probabilistic channels in a patch of membrane gives rise to the continuous shape of the action potential.